Okay, so now we're ready to talk about cross sections that are different than circles. In the last couple videos, we focused primarily on those cross sections being circles, and we dealt with the area formula of pi r squared, manipulating it accordingly to the functions that were given. So to just kind of refresh your memory, we know that our volume is going to be the integral from a to b of a of x dx, where this a of x was a cross-sectional area, and as I pointed out in the last several examples, was always that circle. But now we're going to view it a little differently. We're going to view this problem now with cross-sectional semicircles, squares, and equilateral triangles. So in this particular problem, we're going to find the volume of the solid whose base is enclosed by the unit circle and whose cross-sections are taken perpendicular to the x-axis as semicircles, squares, and equilateral triangles. And so you can see these cross-sections are in fact perpendicular to the x-axis. Okay, each of these perpendicular to the x-axis. And that's going to be important as we set this thing up, so that the problem gives very, very clear instructions on what we need to do. All right, so part A. Part A wants us to use semicircles, which means that our a of x formula would need to be 1/2 pi r squared. Okay? Now, we know that from being given, we're enclosed by this guy here, that this not being a function we can't use directly, but instead we're going to need to view this as y equals plus or minus root 1 minus x squared. Okay, so we got to have a function that we're able to drop in there. Now, for this particular part, our a of x now would need to be from 1/2 pi, and that radius now you can see how that would need to be our function plus or minus root 1 minus x squared squared, just like it was in the last section where we dropped that function in there. It happens to be squared, and so our volume would now be the integral from -1 to 1, remember it's the unit circle, pi over 2 times 1 minus x squared dx. So this would be our setup now using semicircles instead of actual full circles like we have in the past. So number B over here, now they're wanting us to use squares. So for squares, I'm going to go ahead and draw a picture similar to what they have, one hopefully that's a little bit easier to see though. So this picture that they have drawn, okay, you can see one of the most important parts of this picture that they have drawn is that this would be a y and this would be a y as well. And so I'm focusing on the y's because I want to be able to take advantage of the fact I'm using this guy right here. So when it comes to the area a of x of this guy, that's going to be our 2y squared. We know it's a square, so it's going to be the length here, which is 2y, and then it's going to be squared, which gives us then 4y squared. And in reality, this isn't truly a function of x if it's got a y there, so I would have to substitute that inside of it. So now we would have our true a of x being a 4 times 1 minus x squared, just like the last one. So our volume is now going to be the integral from -1 to 1, 4 times 1 minus x squared dx. So this was the first one where we've dramatically changed the a of x formula. We're focusing in on a square, nothing to do with a semicircle or a circle like we have in the past. But that's okay, it's the same idea. We want to figure out how to write our area in terms of the variable that we're searching to substitute in for, to take into consideration, of course, the actual function that's been given in the problem. So there sits this guy right here. Okay? Part C. Part C is going to require a little additional work, but it's not too bad. I'm going to start it the same way as I did Part B in drawing a picture, hopefully similar to what you've seen or what you see up in the screen. Now pay close attention to how I'm drawing this. I'm drawing this so that we've got our equilateral triangle here coming up the x-axis. Okay? In drawing that now, since it's equilateral, if I call this guy right here 2y, then this would have to be a y, and that would have to be a y. Okay, it's got to be the equal length on all sides. The reason we label it like that is, of course, so that we can figure out this height as well. So the height would be this guy. Well, using the Pythagorean theorem, our height can be found by taking y squared plus the height squared equals 4y squared. So the height squared equals 3y squared, and the height equals root 3 times y. So this guy here would be root 3 times y. Now, the area, I'll call it a of x, even though there's not going to be an x in there just yet, but hopefully it'll remind us where we want to go, is going to be 1/2 base times height. The area of a triangle is 1/2 base times height. The base would be this guy right here, so 2y, times the height, which we have right here, which is root 3y. So then if I put this together, I'm going to have a root 3 times y squared, and now when I truly drop my x in there, that's going to be that 1 minus x squared again. So for our volume, we would get -1 to 1 root 3 times 1 minus x squared dx. So if you've taken a little bit of time to watch this, I would encourage you to now pause the video, take a little more time, and really study hard what we've done. It's not any different than the circles that we started with in this section, except the a of x formula is now going to need to be changed to these different cross-sectional shapes: semicircles, squares, and equilateral triangles. I would also encourage you in particular on part B and C to study these pictures a little bit to see where they came from, because that was the driving force in then labeling and also then simplifying down to come up with our function that we needed to plug in.